Hi everyone, I'm Sital and this is my colleague Sergey. We work at Facebook and the Big Compute team. And today we are going to be talking about tuning Apache Spark for resource efficiency. As Spark is being widely adopted at Facebook, we are constantly striving to improve the efficiency, scalability, and performance of Spark. Along the same line, we embarked upon a project recently to improve the resource efficiency of our Spark jobs. So in this talk, we are going to be talking about what resource efficiency means, what can make your Spark jobs resource inefficient. We'll take some examples and try to explain what resource inefficient application can look like. And then we'll talk about our history-based resource auto-tuning project, which is deployed in production and that can save a lot of resources for us. And at last, we'll share some results. Before digging into the problem, let's take a high-level look at the Spark execution model. On a very high level, this is how your Spark job looks like. We have a Spark driver, which acts as a central coordinator. It talks to the cluster manager, which can be Yarn, Mesos, or any other customized cluster manager you can have. The Spark driver launches a bunch of Spark executors on the cluster, and each executor is a JVM, which can be multi-threaded, and each task of Spark task runs as a separate thread in the JVM. So you can see the resource request sent from the Spark driver has two components. One is CPU cores, and second is memory. The CPU core is controlled by the Spark executor core Spark configuration, and the memory is controlled by Spark executor memory. Of course, you can have multiple Spark applications running at the same time in the cluster, and you will have multiple Spark drivers, and in that case, you can tune each and every Spark application. Take a look at what Spark task is. A Spark task is a minimum unit of execution which is executed by the Spark driver. So whenever you submit a Spark job, then your input is split into multiple smaller chunks we call split, and each Spark task processes that small split. So the execution model of Spark is such that we allocate minimum one CPU core for the task. So if you have a 4 CPU core machine, then you will at most be running 4 Spark tasks on that machine at any point of time. This is fine as long as your Spark tasks are actually consuming the CPU, but if your tasks are I/O bound, it might lead to significant wastage of CPU. We'll talk about this problem in details later. So let's define some Spark CPU efficiency metrics. First is CPU time. CPU time of a process we define is as a aggregated CPU usage over time. So for example, in the graph you can see we are plotting the CPU utilization of a process over time, and the area under the curve is actually the CPU time of that process, right? And so you can see some diffs in the graph, and the diffs might be corresponding to the time where your process is actually spending time doing some I/O. And for a Spark job, when we are talking about CPU time, because the job can spawn multiple executors, the CPU time of a Spark job is just an aggregated CPU time across all the executors. Next is CPU reservation time. CPU reservation time is the CPU allocated from the perspective of the resource manager. So CPU reservation time can be different from the CPU time because your job might allocate a bunch of CPU, but it might not be using them. And that's why we define the CPU efficiency of a job as the ratio of CPU time and CPU reservation time. So if a CPU efficiency is 1, which is the ideal case, then your job is using all the CPU cores allocated to it. But if it is less than 1, it means that you are allocating a bunch of resources, but you are not using them. And now let's take an example of what can make a Spark job CPU inefficient. We have a very simple query over here. Basically, what it is doing is it's reading a big table and sorting all the rows by a particular column and inserting the data into an output table. Right? So on a very high level, the job will be split into 2 stages and will have multiple sub-stages as shown in the figure. We'll not go into the details of each and every sub-stage, but we can see that we have 7 sub-stages, and 5 out of 7 sub-stages are actually IO-intensive operations. Basically, these IO-intensive operations are because the job might be reading a lot of data, and then you are doing a lot of disk IO or network IO in that case. So for a CPU inefficient application like this is how your graph of utilized CPU and reserved CPU will look like. We can see there is a significant gap between these two, and that's how you are reserving a bunch of CPU but not utilizing them. So why does CPU efficiency matters at all, right? So this is a real life example of one of our cluster, and the blue line shows the reserved CPU time of all the jobs running at any point of time, and the orange line is the CPU time. So we can see there are many point of time we actually have the reserved CPU time is 100%, but the CPU time is significantly less than that. What we mean is, from the cluster manager perspective, the cluster manager thinks that the cluster is fully scheduled and there is no more room for running any job, but we are not actually utilizing all the CPU resources available in the cluster from the system perspective. And this will lead to high backlog on the cluster. Backlog we are defining by as the number of jobs which are waiting in the cluster manager queue. So because the cluster manager thinks that cluster is fully scheduled, it will not allow you to run more jobs, but you actually are not using all the resources available from the system perspective. So the solution we are proposing is CPU oversubscription. What CPU oversubscription means is we want to, instead of allocating 1 CPU core per task, we want to be allocating a fraction of CPU core for task. So for a machine with 4 CPU core, you will be able to run more than 4 tasks at any point of time. So please note that fractional allocation is just a logical allocation from the perspective of resource manager or cluster manager. There is no physical fractional allocation here. So as you can see in the graph, like after allocating a fraction of CPU core, the gap between the utilized CPU and the reserved CPU will go down, and that's how your application will become more CPU efficient. Now let's talk about Spark memory model. On a very high level, this is how your executor memory looks like. So the executor memory pool is divided into 4 memory sections. We are not going to be talking about these sections in details, but each section over here has its own purpose, and they are used for a specific purpose. The Spark executor JVM is spawned with XMX equal to your Spark executor memory. And at any point of time, we might be running multiple tasks on the JVM, and all the tasks share the memory pool available in the JVM. From the cluster manager perspective, however, the cluster manager allocates little more memory than the XMX of the JVM. We tend to leave a little overhead, little room for the overhead, like overhead might be because of native memory, your stacks, and JVM execution overhead. We leave around 7 to 10% of overhead. So there is the cluster manager allocation is more than the XMX of the Spark executor. Next, let's take a look at memory efficiency metrics. It's very similar to CPU efficiency metrics, which is the ratio of the memory utilization from the perspective of the operating system versus the memory utilization from the perspective of the cluster manager. Similar to CPU inefficient application, you might have memory inefficient application which might be allocating a bunch of memory resources, but they might not be using it. And now let's take an example of how a memory inefficient application will look like. So we have a very simple query over here. The query is just counting the number of rows from a table. So we'll have the Spark job will have 2 stages. The first stage will just scan all the rows of the table and calculate the partial sum. And the second stage will send the partial sum to the stage 1, to the task in the stage 1, and calculate the final sum, final count, row count, right? So in this case, the shuffle memory is used only to store the sum. Sum, it might be an int or long, but basically it will not take more than few bytes, right? So, but if you are allocating high amount of shuffle memory for applications like this, then you are basically wasting that memory. Of course, for a memory inefficient application, you will be able to kind of tune those applications. The various memory configurations are available. Fortunately, Spark has so many knobs to tune that you can tune those knobs like XMX, your memory overhead, or memory fraction to make your Spark application more memory efficient. But tuning each and every parameters and for each application is kind of not scalable. So instead of doing that, what we resort to is oversubscribing the memory. So the high level idea is reserving as much memory as needed by the application. So we might be able to reserve memory which is less than the XMX of the Spark executor. So please note that memory oversubscription is not as safe as CPU oversubscription. If you are reserving less than the XMX of the executor, then it might be possible that it might lead to several side effects, like your executor might start using more memory, and then you might see some executor kill, or also it might make your cluster unstable. So it has to be done very carefully, and we'll talk about how we are doing the memory oversubscription later in the slides. So after memory oversubscription, we can see that the gap between the utilized memory and the reserved memory is lower, and we are actually reserving, we might be reserving less than the XMX of the executor. So to summarize what we talked so far, we discussed that there are different kind of application, and not a default setup configuration or one setup configuration fits the need of all the application. If you are using a default setup configuration for all the application, you might be wasting a bunch of resources. And we discussed CPU and memory oversubscription technique, which can make your jobs more resource efficient. Of course, you can run the jobs individually and take a look at the resource usage, and based on that, you can tune various parameters to make your jobs more resource efficient. But in our case, where we are running like thousands of unique jobs daily, it's just not scalable for us. So instead of doing that, what we resort to is auto-tuning of our resource for our jobs. So we have many jobs in our cluster which are periodic by nature, and the resource usage pattern of those jobs do not change over multiple runs significantly. So what we can do is we can take a look at the resource usage of the jobs in past, and based on that, we can try to predict what is going to be the resource usage pattern like in the next run. And based on that, we can try to tune the resources for the job to make them more resource efficient. So next, we're going to be talking about history-based resource auto-tuning, and I'll hand over to my colleague Sergey to talk about it.
Thank you, Sital. So let me dive deep into history-based resource auto-tuning that we implemented here at Facebook. So just to recap, the high-level idea is that most of our workload on our clusters is generated by periodic jobs, which are running on a predefined schedule. And for each periodic job, we want to predict memory and CPU requirements per executor based on utilization in previous runs of this job. And then we want to request containers from cluster manager based on the prediction. Now let's have a look at how we actually can achieve this. Here is an example of a standard container, let's say yarn container, that has a Spark executor running in it. The Spark executor has configuration predefined like this. So the number of cores is equal to 4. Spark task CPUs is equal to 1. And this essentially means that we can run at most 4 divided by 1 number of tasks, which is 4, in parallel. And the heap size, the Spark executor memory, is equal to 8 GB. Now, in a classic approach, we would be requesting at least 4 CPU cores and 8 GB of RAM for such an application. Now, let's have a look at what if the executor is actually not needing that much of resource. So you can see, like on the right side, there is a container which has 3 CPU cores and 6 GB of RAM. But we are still actually running the same executor with the same configuration. So it will be running 4 tasks, and the heap size will be 8 GB. If we actually can guarantee that the heap size will not be reaching more than 6 GB of RAM, we can actually run this executor pretty safe. Now let's have a look at a simple example of a machine with 12 CPU cores and 24 GB of RAM. With the first approach, where we had 4 CPU cores and 8 GB of RAM, we will be able to pack only 3 containers in this case. And if we actually apply oversubscription of the resources, we'll be able to run 4 containers, and we can run 16 tasks in parallel at the same time. So there are, of course, some cluster manager requirements in order to be able to achieve this. And in the previous examples, I was giving when we were cutting CPU by an integer number, by 1. And we came from 4 CPU cores to 3 CPU cores. This is not always going to be the case. And in some of the cases, we might be cutting CPU cores by some fraction, by 10%, 15, 20%. And in this case, a cluster manager has to allow fractions of CPU to be allocated. So something like 3.6 cores instead of 4 cores. Also, a cluster manager has to periodically log resource usage statistics per each container. And this data will be used in the predictions later. The architecture looks pretty straightforward. So we have 2 independent phases. The first phase computes and persists predictions for memory and CPU utilization per executor for each of the periodic jobs. And this is going to be done on an hourly basis. And the second independent phase is actually applying the predictions from the Spark driver when job launches and needs to request additional resources from the cluster manager. Let's look into the simplest part over here. So how we will actually be applying this. In the middle, you see there is a Spark driver. And in a classic scenario, we'll be requesting resources based on Spark CPU cores and Spark executor memory. But here, before actually doing that, we'll be fetching the predicted CPU and memory required per executor for the application from some data source, and let it be MySQL database. And then we will request the resources from the cluster manager based on the prediction. Now, computation and persisting of predictions is going to be done on an hourly basis because, as I said, we have a lot of periodic jobs, and different jobs are landing at a different time. And here in this picture, you can see that there were 3 runs of the prediction algorithm, and this is done in order to pick up the jobs which landed in the last hour. So like the first computation will pick up the 3 fresh runs of the jobs. The second computation will take into account only 1 job, which finished within an hour. And the last round of the predictions will take into account 6 fresh job runs. So what are the inputs for the predictions? For each periodic job run, we will need CPU time and CPU reservation time, which Sital spoke about. We also need executors maximum use memory statistics. And we also will need a job identity hash to distinguish between runs of the same job. Now let me dive a bit deeper into what job identity hash is and why we really need it. There are 2 types of periodic jobs, SQL queries and some applications. In our case, it's Scala applications. And if you change a query or Scala implementation, it can actually significantly change memory and CPU footprint. And this is true not only for the implementation. Same is true for configurations of memory and CPU and other Spark configurations like Spark SQL shuffle partitions, which defines the number of reducers. And so the job identity hash will represent a state of job's implementation and configuration. And let me give you a very simple example on a SQL job. So here is a simple SQL query which selects some data and inserts into a table. This job will have an identity hash 1, 2, 3, 4, 5, 6. And it's inserting into partition with date equal to yesterday. Oh, actually, yesterday last year. And let's consider that like the same job is running on the next day, and this time it's actually inserting into a different partition. It might be running on a different set of data, but and it will be inserting this into a different date partition, but we still consider this job as the same, and identity hash doesn't change. But it's also possible that we will make significant changes to the query, and in this case we are inserting into a different table. And we are doing some group by. And this can actually change the CPU and memory footprint significantly. And that's why we are changing the identity hash of the job. And now let's look into the prediction algorithm. And predictions are computed for each job identity hash separately. And for each run in the past 10 days, we obtain CPU and memory usage aggregates. And for memory and CPU, we are doing this a bit differently. For memory, we take P99 of max used memory bytes across all the executors which ran on the application. And for CPU, we'll be taking total CPU time divided by reserve CPU time and multiplied by the actual number of CPU cores that we were requesting for each executor. So you can see that we are going much more aggressive on the CPU. And it's very similar to like an average CPU cores which we are using on the application. With the memory, we have to be much more careful because we cannot essentially oversubscribe memory, because if you give less resource than job actually needs, the job can be killed. And next, we do separately for CPU and memory the following steps. We sort values in ascending order, do line smoothing to avoid outliers, and take P90 of values. And this is what's going to be used in the next run of the job. So the algorithm is pretty linear, but it's obtaining pretty good results for us. So what are the potential issues? So we can because we are oversubscribing CPU, we can have an increased CPU time due to context switching. Let's say if you had like 4 tasks running on 4 cores versus when you run those tasks on 3 cores, you will actually have more contention for the CPU, and you will have more context switching. And containers could also be killed by cluster manager if used memory exceeds the requested amount of memory. So let me talk more about the container kills and how they actually happen. Periodic jobs are not exactly the same. So the reason why it can actually happen, even though we have some predictions, is because they run on different set of data. And so let's say memory usage can go up compared to previous runs of the same job. In a classic approach, cluster manager kills container if memory usage goes over the limit. We could have some buffers out there, but still, like if it goes beyond the limit that we actually request, it will still be killed. And here is a simple example. So we have a physical machine with 24 gigabytes of RAM, and we have 2 containers running out there. The first one looks pretty healthy, but the second one is going over the limit by 200 megabytes. And even though we have a lot of free memory, we have 8.2 gigabytes of free RAM, this container would still be killed by the cluster manager because it's exceeding the resource quota. Now, let me describe how we actually reduce the container kills on the cluster manager side. So we want to allow containers to go over the limits. And we'll be killing containers mostly when the machine is actually running out of memory. And in this case, we'll be killing the highest offender. Here's a very simple example. So let's consider we have very low load on the cluster. And we see 2 containers are running, and each of them is going over the limit with the ratios of 1.1 and 1.2. And we still have 5.6 gigabytes of free RAM. And in this case, like we'll just allow these containers to keep going. But what happens if there is a very high load on cluster and we have like all the containers packed on this machine? And in this case, you see that we still have our 2 containers which go over the limit. And we also have another container which doesn't go over the limit. And machine is running out of memory. We have 0 gigabytes of free RAM. And we need to do something because in this case, we can actually impact all the containers which are running on this machine, and it can actually impact all the applications, many applications. So in this case, we will kill the highest offender, the one which goes over the limit the most. So how else do we reduce container kills? So we introduce a threshold for maximum number of container kills due to resource quota exceeded. And when number of container kills exceeds the threshold, we dynamically disable resource tuning while job is still running. And in the next iteration of prediction computations, we will take the higher memory usage into account. Now let me share the results, and first I'll speak about improvements in cluster metrics. Here is the graph which shows the allocated CPU percentage versus utilized CPU percentage. The blue line is basically what we give from the perspective of the cluster manager. And you can see that we were actually oftentimes capping at the CPU. So if you allocated all the CPU cores, even if you have like half of the memory on the cluster free, you cannot allocate any more containers. And the gap between utilized and allocated CPU percentages was actually pretty big. After we rolled out the change, we could see significant improvements. So we were no longer capping on the CPU, and the lines are actually look pretty much identical. Now let's look at the similar graph for allocated memory percentage versus utilized memory percentage. We were never capped for this cluster on the memory, but still the gap was very huge. And on average, the memory utilization was around 50–60%. After we rolled out the change, things looked much better. So reservation actually went down significantly, and the gap between utilization and allocation went down. Cluster backlog. So this is the number of sessions which we're waiting for in the queue for the resources. And this actually also improved for us significantly. And similar graph for the resource waiting time. This graph shows how much time a job was waiting for the executor for the first executor to be allocated. And this time went down as well. And we also had some improvements in performance of jobs. How comparison was made? So we took two 3 days length segments, one without auto-tuning enabled and the other with auto-tuning. Defined a set of common jobs that ran during both segments, and there were actually over 1,000 jobs like that. And for each segment, we computed averages for key metrics, such as CPU time, CPU reservation time, memory reservation, and etc. So CPU reservation went down by 22% for those jobs. Memory reservation went down by 25%. And also, actually, like we could see some negative impact on the CPU time. The average CPU time increased slightly by around 15%. But we think it's totally fine for us because we could decrease the resource reservation much more. And we didn't actually optimize for job latencies because like we shouldn't be inherently impacting this. If we had unlimited resources on the cluster, we wouldn't see such improvements. But we could see the improvements in the average job latency by 40%. And this is largely due to the fact that we decreased the average resource waiting time. Thank you. Questions?
Question. Have you considered using a machine learned model for predicting the resource usage?
Yeah, that's a very good question. That's something, this is probably first phase of the project, and going forward, we want to utilize machine learning to kind of learn the CPU and memory usage and predict for new jobs, as well as this kind of method has currently as a drawback that we don't use it for new jobs, right? New jobs, we don't have the history. So if we can learn it based on some similar jobs, we can probably leverage it for new jobs as well.
That's what I was thinking. Thank you.
Thank you.
Yeah. My question is, usually you specify the executors and memory during Spark submit, right? With this auto-tuning prediction, do you do it when the resource manager is asking for the request? You don't have to specify during the Spark submit?
So your question is, why do we need to specify Spark executor memory?
Do we need to specify those parameters for the job in Spark submit, or do you do from the driver to when asking for the resource manager? Where the hook is?
We kind of wrote a shim like between the driver and the cluster manager,
Okay.
where our predictor lives, and then it is kind of intelligent enough to kind of change or tweak some of the configurations and not ask for the Spark executor memory configuration from the cluster manager.
Okay, so when the driver asks for
Right.
the resources, that's...
Yes.
Hi. Are you gonna, hello?
Sorry.
Sorry, real quick, we're out of time for questions of sessions. If you'd like, they can go ahead and take questions offline afterwards. Let's give them a big round of applause.